Hey everybody, welcome back. We're on chapter 3. We're going to be talking about frequency distributions and visualizing data. First, a little bit of review from last chapter. I hypothesized that daily exercise is associated with lower resting heart rate. Heart rate, measured in beats per minute, is an example of what kind of scale of measurement? The answer is ratio. Why is that? Well, first of all, it's a number, right? Beats per minute is a number, so it's not nominal, that's just categorical data. It's more than ordinal because not only can you put beats per minute in an order, but each beat is equally spaced, so it's even more than interval. It is interval, but it's even more than that. It also has a true 0 point, and that is one thing that all ratio variables have. You could have a resting heart rate of 0. Unfortunately, that would be associated with a lack of a heart rate. So you can figure out what would be happening to you in that moment. Okay, let's move on. Okay, so chapter 3 is all about visualizing data. And there are two main ways we can visualize data in psychology. First one is tables. We've already been using some tables. The second one is in graphs or charts. We're going to say graphs and charts are kind of the same category for the purposes of this class. Now, why are there so many different kinds of charts and graphs and tables and those kinds of things? Well, that's because the type of data you have, which gets back to last chapter, the type of data you have tells you the type of graph or chart that should be used to illustrate it. So let's walk through a number of examples of those. So first, let's define frequency. Frequency is just how frequently a certain score or category for a specific variable shows up in the sample, right? So this is typically, we're talking about what is the number of people in our sample who obtain a particular score, or the number of people who fall into a particular category. And we can get at this first by looking at the table from last time where we say, okay, we got 4 participants. One of them drinks 2 cups of coffee a day. One of them drinks 0. The third one drinks 3. The fourth one drinks 4. Okay, we're adding in also a new variable of eye color. And now that's just a category, right? That's a nominal variable. So the first participant happens to have blue eyes, the second and third have brown eyes, and the fourth has green eyes. Now, those are what we call raw scores. That's exactly what the participant either self-reported, or that's the number that the researcher put directly into their table after the participant told them these things. Okay. But these are not frequencies. This is not, well, how many participants drank 0 cups of coffee, or 1 cup of coffee, or 3 cups of coffee? How many of our sample, how many participants have brown eyes? How many have blue eyes? That's not what this raw score data is telling you. So it can be useful to manipulate the data to actually tell you different kinds of frequencies. So if we want to convert the raw scores into a frequency table, basically, if we want to do that just for cups of coffee first, we would create a new table where the first column is cups of coffee. And this is basically all of the possible amounts of cups of coffee that our participants could have drank. All right. So it goes 0, 1, 2, 3, 4. The next column is frequency, and you can see that, well, the frequency for 0 cups of coffee is 1, because in our original table, only one person had 0 cups of coffee. That was participant number 2. Right? 0 people drank only 1 cup of coffee. No one in the first table says they had 1 cup of coffee that day. And then there's frequency of 1, for people who drank 2 cups of coffee, also frequency 1 for people who drank 3 cups and 4 cups of coffee, right? Then typically what you see in a frequency table is not only just the frequency, the actual number of participants who obtained that particular score or fell into that particular category. But then also there's a column for percentage of the entire sample. We can also make a frequency table for eye color. And what you would do again is from the table on the left, now to the table to the right, you put the first column as eye color, and that's all possible eye colors. Okay, blue, brown, green, hazel, gray. I think amber is also technically another one. And then, well, what are the frequency of our participants who fall into each of those categories, who have each of those colors of eyes? So we know that our first participant has blue eyes. They're the only one with blue eyes. So frequency should be 1, and percentage is going to be 25, that 25%, because that's 1 out of the 4 participants we've got. Now 2 people have brown eyes. That's participant number 2 and participant number 3. They have brown eyes. So that's actually a frequency of 2, and that should be 50% of our sample, because 2 out of 4, right? That's 50%. 1 person has green, 0 people have hazel, and 0 people have gray. Now here's a more realistic example. So participants responded to the question, to what extent do you consider yourself an environmentalist? On a scale of 1, not at all, to 7, very much. What you can see in the first column, the score column, is that they listed out the possible scores on that scale, right? 1, 2, 3, 4, 5, 6, and 7 are the possible scores a participant could rate themselves at. Then in the second column, that's the frequency. So how many people scored themselves as not at all considering themselves an environmentalist? 2 people. 2 people said, I score a 1. I don't consider myself an environmentalist. All right. Then you can see that that corresponds to a percentage of 3.6% of the entire sample size. Now, if you want to figure out what is the entire sample size, you can just add together each of the rows of the frequency. So that would be 2 plus 5 plus 4 plus 8 plus 12 plus 16 plus 8. That'll give you the actual number of people who scored on this particular question. The reason why frequency tables are useful is because you can get a first glance of, okay, well, where are most people located? Like, are we talking about a lot of people score at the low end of the scale? They're not really considering themselves environmentalists in this particular sample. Or are most people scoring at the higher end of the scale? So a lot of people do consider themselves more of an environmentalist. And in this particular sample, remember, it's going to be based on the exact parameters of the group that you recruit for this sample. Let's say these are folks from Boulder. Well, a lot of people actually are scoring at the higher end of the scale, because you can see 12 people scored a 5, 16 people scored a 6, 8 people scored a 7, and only 2 people scored a 1, right? So a lot of people are actually scoring more towards the high end of this scale, which could make sense for the type of sample that you collected here. So let's practice reading this. So what percentage of the sample scored a 3 on this scale? That's going to be 7.3, right? So you go to the score of 3, 4 people got that score, and 4 out of however many people this is 7.3%. Now, you can also see there's another column I didn't include previously, which is the cumulative percentage column. I mostly don't pay that much attention to this in my own research, but it could be useful. For instance, it can tell you, well, overall, what percentage of people scored either a 3 or lower? You would say a 3 or lower. Well, that's going to be 20%, because you go to score of 3 all the way over to cumulative percentage. Same thing if you want to know how many people scored a score of 6 or lower. That's going to be 85.5%. Now let's expand this a little bit. Okay, so we know about frequencies and frequency tables. What about frequency distributions? A distribution in statistics, and you're going to hear that word all semester, distribution is just simply a set of scores for a particular variable. A frequency distribution is not just those raw scores, but it is the distribution of the different frequencies. So you could make a table like we just made, and then you would actually try to graph each of the numbers in the frequency column, and we're going to do that. Now, frequency tables are really, really useful, and you see them all the time in research papers. But at the same time, it can be even more useful sometimes to display data visually by using a frequency distribution graph like this one. So it took the same numbers that we saw in the frequency column and the rating column or the score column from that frequency distribution table and turned it into a histogram. This is called a histogram. This frequency distribution graph, again, it's the same numbers. So you'll remember that participants were asked, okay, on a scale of 1 to 7, to what extent do you consider yourself an environmentalist? And 12 people put a 5. They rated themselves as a 5. And you can see on this bar, if you go to the rating of 5 and you go up, it looks like a count or frequency of about 12 people. 16 people rated themselves a 6, so very much an environmentalist. And you can see again, that's the highest peak, that's the highest bar in this graph, and it does indeed go to 16 in terms of the count. So to create a frequency distribution graph, in this case a histogram, you're going to first, on the x-axis, the horizontal axis, you're going to place all the possible scores for this scale, 1 through 7. On the y-axis, the vertical axis, is frequency or count, right? So how many of the participants obtained each of those ratings from the scale? So again, 12 people got a score of 5, so you would take the score of 5 on the x-axis and mark a score of 12 on the y-axis, and where those things meet, that's going to be the top of the bar for that score. I also want to mention that frequency distribution graphs come in 2 flavors. The first one that we've seen is a histogram. Histograms are the term for graphs used with quantitative data, like interval or ratio data. All right, these are numbers. Notice that in a histogram, the bars are touching, right? This looks like a bar graph, but the bars are touching because there's some continuity from each of these numbers to the next number in an interval or ratio data, right? Bar graphs, on the other hand, are for categorical or nominal data, or sometimes ordinal data. All right? Notice that the bars do not touch because these are not continuous numbers. Each of the bars is very different. It's a different category than the bar next to it. So we can see in this graph, we're talking about the number of students who have gotten an A, a B, C, D, or an F on a particular exam. So let's talk about the types of graphs that you might use for nominal or ordinal data. So as I briefly mentioned earlier, when you have nominal or ordinal data, that's categorical types of independent variables, you can present them as pie charts, which could be really useful. So this example here is a nice pie chart that has ordinal data. These are freshmen, sophomore, junior, and seniors. So the actual independent variable here, the ordinal independent variable would be year of university, right? Like year of schooling. And you can break that down into these 4 different subcategories, freshman, sophomore, junior, senior, and then just tell me either the whole number of each of your participants that fall into those categories. There's 100 freshmen, there's 300 sophomores, there's 87 seniors or whatever, right? Or in this case, pie charts are oftentimes used to show percentages. Sometimes you'll even see the absolute numbers and the percentages for each pie slice at the same time. But this one's presenting, okay, it looks like 52.36% of this particular sample of undergraduate students are sophomores. So that takes up the biggest chunk. And obviously the size of the pie slice is representative of the percentage that subcategory takes up. These are really useful, but you don't see them actually super commonly in scientific manuals. But you don't actually see them all that commonly in scientific manuscripts. Now, you definitely want to look out for some of these things, not make these mistakes yourself, and also look out for mistakes that other people publish or post on blogs or on the internet anywhere. So what is wrong with this pie chart? There's numerous things wrong with this pie chart. Well, the first thing is these percentages don't add up to 100%. They're more than 100%. Ask yourself, uh, what percentage of a pie could you possibly have? You could have 100% of a pie, right? You can't have more than 100% of a pie. I wish you could. I love pie. But no, they're saying that 50% of people in this sample own dogs, 30% of people own birds, 40% of people own cats. The problem with this data is they're not mutually exclusive because people can own multiple different kinds of pets, obviously, right? So already they're in trouble because you want to use categories that are mutually exclusive, therefore all of them combined do add up to 100%. And finally, the pie slices are not representative of the percentage of pet owners in each of these subcategories, right? So dogs, if 50% of people in the sample own dogs, that pie slice should be half of the pie to be 50%. So obviously there's a lot of things messed up with this. It's an affront and a crime against math and statistics, and the owners, or no, the creators definitely should go to jail for that. Here's another pie chart that shows you the breakdown of, on a single exam, how did students do on that exam? And the first problem I would say is, well, there's no percentages associated with these pie slices, right? It would be really helpful to know, even though visually I can see that the majority of the class got C's, and very, very few people got A's, very few people got F's. I'd like to know the actual percentages of those as well. Earlier, I mentioned that some types of data, like nominal data and sometimes ordinal data, can also be presented in a bar graph. And so what you're seeing here is actually the exact same data. Pie chart on the left, bar graph on the right, but both of them show you that on the whole, most of the students for this exam received a C, right? Fewer B's and D's, and even fewer A's and F's. So you can look at this a couple different ways. And so continuing on with these bar graph examples, very similar example where we are having the percentage again of freshman, sophomore, junior, and senior in a particular sample. So the percentage is on the y-axis, the year of schooling is on the x-axis. So this is a ordinal, qualitative type of variable, of independent variable, whereas percentage, that's continuous, right? Now, when you're reading a bar graph, you only really want to pay attention to the height of each bar. This is displayed kind of awkwardly because the percentages are like in the middle of each of these bars. Normally speaking, that's not really how it would go, but that's just how you see it sometimes in SPSS and some other software. But really, you pay attention to the overall bar height, and that's going to tell you the percentage, or that might tell you the average height of a sample, or the average happiness of each subcategory, or something like that. So far, we've only seen simple bar graphs, which just for each subcategory have one single bar. You can also see what's called clustered or grouped bar graphs, and basically that's splitting subgroups into even another group. And so now you're thinking about two different type of groupings at the same time. So this is a graph of ethnicity of students in the student body, but within each ethnicity is also broken down into male and female. So there's, you're thinking about ethnicity, but you're also thinking about gender. And this can be shown in a lot of different kinds of ways, but just for example. You might also see on some bar graphs these little bars sticking off the top of each of the bars in the graph. And what is that all about? Well, in psychology, if you're trying to get bar graphs published, typically they want to see what are called error bars in your bar graph. And so for each category and each bar you have, they've got these whiskers, these error bars sticking above and below. And that's basically a measure of kind of like variability or confidence that the mean of that bar is accurate. And there's a lot of factors that influence how confident you would be that each of those means of each of those bars is accurate. And so really, really large error bars means you're not very confident that the mean of that bar, that the height of that bar, is exactly where it should be. Really tightly, very small error bars mean that you are more confident that this number is probably right. But we're not really going to go into that for this class. If you go to grad school or if you're interested in statistics, you'll learn much more about confidence intervals. So I looked pretty hard for a meme of a chart or a funny graph or something, but as you can imagine, it was kind of hard to find something. This one is okay. But for those of you who have made it all the way to the end of this lecture, I'm going to give you an extra credit opportunity. If you add a funny chart or something that's attached to a meme, it's a chart, it's a graph, it's a table, whatever, and it's a humorous meme type of situation, and you upload that into the extra credit assignment for this week, I will give you an extra credit point. All right, that's it for this one. Have a good day. I'll see you in the next one.